Hello, everybody. Welcome to the 2016 Clay Lecture. I'd like to make a brief remark about our guest of honor, Landon Clay, and we'll be joined by his wife, Lavinia, shortly. The Clays are generous supporters of intellectual work. Their principal interest actually is not astronomy. It's mathematics. They founded the Clay Mathematics Institute, which was originally in Cambridge, but is now in Oxford, England, and is a very significant supporter of mathematical research and the encouragement of careers of budding young mathematicians. I think it's 4 out of the last 5 field medalists have spent a portion of their career with Clay Mathematics Institute support. In addition, there's a list which you should look at if you haven't already of the famous Clay Millennium Problems. And there's a prize for solving each of these. And it includes some well-known, like the Riemann hypothesis and the Poincare conjecture. And the Poincare conjecture actually was resolved by Perelman in St. Petersburg. But that's a very complicated and long story that we won't have time for here. Fortunately, Landon also has been very supportive of astronomy, especially astronomy here. Those of you who are regular observers have probably spent time at the Clay telescope at Magellan. We love both of the Magellan telescopes, but the Clay is actually seriously oversubscribed. I mean, there's a lot of competition for time on the Clay telescope. Landon also invested, when it was a very speculative, high-risk investment, in the development of the first primary mirror segment for the Giant Magellan telescope. Back when it wasn't even clear that the Mirror Lab would be able to polish the surface to this off-axis parabola that was necessary. And in fact, there was a period of time where we wondered if it was going to be possible. That mirror took about 6 years to polish. But eventually it succeeded. And it was the very generous contribution of Landon that actually really got that started. Landon also supports the Clay Fellowship at the Center for Astrophysics, and these are fellowships that are intended to support the brightest people who are coming out recently graduated from PhD. I mean, typically within a few years. And the intention is to have a fellowship of sufficient duration that somebody can take on a challenging project without the sense of time pressure that comes with a great many postdoctoral positions. So there's been a very significant number of very interesting people in these positions, and part of the requirement, of which there are few, is that each of the incumbents gives a lecture. And it's now Christian Johnson's time. Christian grew up in Houston, Texas, and attended the University of Texas at Austin, and worked with Katie Pilachowski at Indiana. From there, he came here. He spent a period of time, with Michael Rich at UCLA, after which he came here as a Clay Fellow. And we're going to hear from him today on Signatures of Creation, the chemically diverse stellar populations in massive globular clusters.
Well, thank you for having me here today. So I was always interested in astronomy, but it wasn't really until I took my first stellar astronomy class as an undergraduate that I became really interested in stars, stellar spectroscopy, and chemical abundances. For whatever reason, before I took that class, it never really dawned on me that when we say stars are mostly hydrogen and helium, that they're also partly all of the other stable elements on the periodic table. And the thing that really drew me to the field was that we can use particular combinations of these elements that are produced by different stars over different time scales and different environments, and we can actually use those properties to figure out either the current evolutionary state of a single star, or if we look at groups of stars, we can figure out how long ago they formed, where they formed, and we can actually use this information to sort of reconstruct the formation history of systems like Omega Centauri here, which is the most massive globular cluster in the galaxy, or we can even try to figure out how even more massive systems like the Milky Way were assembled. So today, the Clay Fellowship is actually a very wonderful opportunity. As Charles said, it gives the fellow a lot of time to work on a very challenging project. And it's enabled me to work on several different very interesting projects. And today I'd like to talk a little bit about one of those projects that I've been doing in collaboration with Andrea Dupree here and Nelson Caldwell, and also with Mike Rich at UCLA. And what I've been trying to do is take spectra of lots of stars in some of the most massive globular clusters and see if they actually look like the simple stellar populations that we once thought they were. So before I move into sort of the main details, I wanted to start with asking what are some of the big questions that we try to answer with stellar population research, and why are globular clusters important? So one of the biggest questions we try to answer is, how did the early universe and galaxies form and evolve? So in other words, how did the universe start off as sort of small density fluctuations and evolve over the several billions of years to become these very complex organized systems like globular clusters, or star clusters, and galaxies? And globular clusters are very important for this kind of work because they're among the oldest objects, single objects, still in existence. So we know that most of the globular clusters in both our galaxy and in many other galaxies formed during the first 1 to 3 billion years after reionization. So they preserve some very intricate details about the early environment in the universe. So sort of a related question we want to ask is, how were galaxies assembled from these sort of primordial clumps and merger events? So globular clusters are important for a couple of reasons. The first is that we think that they're equivalent in mass to some of these primordial clumps that merge together to form much more massive systems like galaxies. But one of the really interesting things is that globular clusters exist in both massive galaxies like the Milky Way and also in much smaller satellite dwarf galaxies. And if we can use stellar spectroscopy or kinematics or some other related information to separate or distinguish between which clusters formed in our own Milky Way versus those that were accreted, then this actually gives us some very interesting clues about past merger events. And there's also a much more pragmatic reason for why we care about globular clusters. So they tend to trace very intense star formation events, where there's a lot of star formation happening in a very short period of time. But most importantly, they're very bright, very dense objects. So we can actually see individual globular clusters out to distances far greater than we can look at individual stars. And when you're looking at a system like a globular cluster in integrated light, you really need to know the details of this system in order to properly interpret integrated light observations and at higher redshift. So a simple question you can ask is, what exactly is a globular cluster? So this is probably the picture that comes to most people's minds when I say globular cluster. It's some sort of object that looks like the top left picture. Basically a collection of something like a few tens of thousands to a few million solar masses of stars that all formed in sort of a rapid burst, where all the stars have the same age, the same heavy element composition. At this point in time, there's no dark matter, no recent star formation. This is as close as you can get to a simple stellar population. And that's actually kind of a myth that they're a simple stellar population, but it's justified in some part because of the early color magnitude diagrams that we saw. So when you make plots of B minus I versus, or B versus B minus I, you see really only a very simple sequence of stars. So as stars age, they evolve up off the main sequence and up the red giant branch. And if you look at stars at all sorts of different evolutionary states, if you measure their composition, so say you measure an iron abundance, well, a star up here will have the exact same iron abundance as a star down here. Now you'll notice that I said they have the same heavy element composition. Now that's not necessarily true for the lighter elements. So elements like lithium, carbon, nitrogen, as stars evolve up off the main sequence and up the giant branch, because of changes in the structure of the star and increasing temperatures in the center of the star, the lithium and carbon abundances actually decline and the nitrogen abundance increases. But heavier elements like oxygen, sodium, magnesium, aluminum do not change. So if you compare stars at different evolutionary states, you really have to be careful which elements you're looking at. So as I said, elements such as oxygen, sodium, magnesium, aluminum are basically do not change as a function of evolutionary state in a low-mass star. So when we measure, say, an oxygen or a sodium abundance in a star today, it represents the initial composition that the star formed from initially. So one of the things people did as we were starting to do high-resolution stellar spectroscopy in halo stars, globular cluster stars, in sort of the late 70s, early 80s, they said, well, we know that stars in the galactic halo they're very similar in age, similar in overall metallicity to stars in globular clusters. So what happens if we actually look at their detailed chemical composition and compare them? So if they were the same, that could imply that they were related in their formation. Perhaps globular clusters were disrupted and actually ended up creating some of the halo. So when we look at halo stars, we see that they have relatively high oxygen abundances and relatively average sodium and aluminum abundances. So a comment I want to make about these kinds of plots is that this is a logarithmic scale comparing abundance ratios of something like sodium, aluminum, or oxygen. And when I use the bracket notation, that's comparing the relative ratio of two elements in a star versus the same ratio in the sun. So the sun is always at 0 in these kinds of plots. And because this is a logarithmic scale, every change of about 0.3 dex on this scale is a linear factor of about 2. So we know that supernovae, or massive stars, tend to produce compositions that are high in oxygen with relatively normal or standard sodium and aluminum ratios, which are close to what we see in the sun. Now, when we look at globular clusters, you notice that there's a significant population of stars that basically completely overlaps with the field halo population. And you'll notice that I've not so conspicuously called these first-generation stars. So if this was the full picture of what we see in globular clusters, this would be a very short talk. And we would basically assume that halo and globular cluster stars were formed at the same time and were enriched by the same types of stars. But the observations that have really told us that globular clusters are much more complex objects is when we found all these stars with very different compositions, which I just sort of in general call second-generation stars. So these have much lower oxygen, much higher sodium, much higher aluminum than first-generation and halo stars. Now, there are a couple of things to recognize about this plot. So the first is, as I said, these elements will not change in abundance as a function of the star's evolutionary state. So a star will not go from down here to up here as it evolves over time. The difference between stars over here and stars over here is that they actually formed with very different compositions. In fact, for an element like oxygen, the range is about a factor of 10, keeping in mind that the stars in these different parts of these diagrams have the same overall metallicity. So if you measured an iron abundance, say, the stars at different ends of these distributions would be exactly the same. So there's really a whole industry in astronomy devoted to figuring out where these second-generation globular cluster stars come from. So the other thing that we know for certain is that there are very specific chains of nuclear reactions that can produce material that is low in oxygen, high in sodium, low in magnesium, and high in aluminum. And I won't go through all the details of these nuclear reactions, but the net result is that oxygen gets converted into nitrogen, the different isotopes of neon are converted to sodium, and the different isotopes of magnesium get converted into aluminum. And as long as you have an environment where material is being burned at temperatures above about 60 million Kelvin, you actually reproduce material that sort of falls along this plot. So one of the early ideas was that, well, we know how to make stars in this blue region. Those are mostly from core collapse supernovae. And if we sort of assume that we know how to produce these most extreme stars, so something like rapidly rotating main sequence stars or intermediate mass AGB stars, they can give off polluted material in a cluster while these stars are still forming, but not increase all of the abundances of much heavier elements. And if you simply mix the gas down here with the gas up here, you actually end up with a dilution curve that closely matches these plots. So that was a simple explanation, and for several years it actually seemed like that was what was going on. But there's a little bit of a kink here. If we look at this plot, this is a compilation of about 15 different globular clusters. If you look at the clusters individually, you'll notice that while they all share the same general shape, the full extent of abundances, the abundance range of elements like oxygen and sodium, is unique to an individual globular cluster. In fact, no two clusters are alike. And at the present, we're having a really hard time reconciling how you can actually produce such similar formation patterns that are not actually the same. So one of the key questions that was addressed early on was, is this actually a uniform distribution of points, or were stars actually forming in discrete star formation events? And oddly enough, it was actually the combination of spectroscopy and photometry that gave us the answer to this question. So as we've now established, light elements in individual star, from star to star in a given globular cluster, have a full range that ranges something like a factor of 10 for elements like carbon, nitrogen, and oxygen. Now this is important because it has a very strong effect on the near UV spectrum of a first generation or a second generation star. So you can see a first generation star will have weak NH bands, second generation star will have very strong NH bands, and similar arguments can be made for OH, CN, and CH. And about 10 or 15 years ago, people realized that there were very specific filters on the Hubble Space Telescope that are actually very sensitive to these changes in light element chemistry. So this was actually a good way to address whether or not we have sort of a continuous star formation event or whether there are very discrete star formation episodes. So here I've selected 6 different globular clusters. These have different ages, different formation environments, different horizontal branch morphologies, metallicities, etc. If I plot sort of a UV ver minus I color and a UV magnitude, this is not a particular combination that is supposed to be sensitive to light element chemistry. So if you were to just look at a plot like this, you would assume, yes, globular clusters are really just simple stellar populations. But what's really interesting is to watch what happens when you select the proper combination of filters. See that no longer do globular clusters look like very simple stellar populations. In fact, you see that many of these clusters have very broadened or very distinct main sequences, red giant branches, or subgiant branches. And one of the really interesting things to note is that not only is every globular cluster different, but that some globular clusters have 2 populations, some have 3, but you'll notice that they're very distinct sequences rather than a broad distribution, which is what you might have initially expected based on the first plot I showed of the oxygen and sodium abundances. So there's another cluster called NGC 2808. It's actually become the poster child for this kind of work. So whereas the other clusters had 3 populations, this one has 5. Excuse me. You'll see that it has what looks like 3 to 5 main sequences, 5 red giant branches, and this has been quite an interesting and difficult problem to crack. But the way we've really figured out what was going on was by looking at a combination of spectroscopy and this photometry. So if you take particular sequences and group the stars together and take spectra of the stars along each of these sequences, you'll find that they actually group into individual populations. So originally what I called the first generation stars would be this red and green group. And you see that they're what I would call helium normal. They have high oxygen abundances, low sodium abundances. Basically, they're identical to what we find in the halo field star population. And these peculiar second generation stars, they're actually further broken up into different stellar populations. And those that are very extreme, so these 3 populations up here are what I would sort of lump together as second generation stars. But you can see that each of these clumps corresponds to a unique chemical composition. So it's almost deceptively complex what is going on here. So you don't just have multiple star formation events going on where you have a mixture of chemical compositions. You actually have individual star formation events occurring, forming stars still with the same overall average metallicity, but with very different light element compositions. And we presently have really no idea how to explain this from a theoretical point of view. So all the early models that use things like intermediate mass HEB stars, pollution from rapidly rotating massive stars, supermassive like 1,000 solar mass stars to explain these different chemical anomalies, they all fail to address all of this long list of observational constraints that we've built up over the last few years. And these are extremely strong constraints. As I showed just with those 6 clusters, if we look at the entire globular cluster population in the galaxy, all of them show these same characteristics. They all have large light element variations that are broken up into very discrete chunks. So even the simplest, what appears to be the simplest globular clusters, were able to form very distinct, different generations of stars. So I won't go into detail about all of these different observational constraints, because that would actually be the purpose of a different talk. But I'd like to draw your attention to this last point, the mass budget. So in order to actually form all these different stellar populations in the correct ratios, the globular clusters that we see today had to have been something like 10 to 100 times more massive when they initially formed. That seems to be the only way that we can get the numbers to work out. So it was along this line of thinking that I thought, well, if the sort of average typical globular cluster has all of this complexity, what do the most massive globular clusters look like? And will they actually give us additional insight into how globular clusters form and evolve? So for this talk, I'll be discussing 2 of my favorite globular clusters. The one on the left is Omega Centauri, the most massive globular cluster in the galaxy. So if you were to plot a cluster like NGC 2808 that I just showed on the last couple of slides, it would look like a single stellar population in this particular bandpass. But you'll notice that Omega Cen shows at least 5 different discrete stellar populations. So this has been known since at least the 1960s that Omega Cen was a peculiar cluster that was able to hold on to the ejecta from supernovae and actually form different generations of stars with different metallicities. And it's a very popular cluster. If you look on ADS, you'll find hundreds, if not more than 1,000 papers on it. My new favorite cluster is this one right here, NGC 6273. You've probably never heard of it, but it's the 3rd or 4th most massive cluster in the galaxy. It's sort of hidden inside the galactic, it's near the galactic bulge, so it suffers from very complicated line-of-sight geometries. There's very strong differential extinction. But you'll notice that these 2 color magnitude diagrams look suspiciously similar, particularly this odd gap in the extended blue horizontal branch, and also this very broad red giant branch. So I thought that as I came here to start my Clay Fellowship, that this would be a really great object to look at. And as I was doing some background reading on it, one of the 5 or so papers that exist about it was a paper in 1999 by Piotto and collaborators, where they obtained sort of the first Hubble Space Telescope images of this cluster. And they noted that it has a very broad red giant branch, but they assumed that this was due to unaccounted for differential reddening. But of course, they have this nice quote that a study of the metallicity of its stars would be worth doing. So 15 years later, no one had done it, so I thought this would be a great project for me to do. And it was at this time that on the Clay telescope, they were installing this brand new instrument called M2FS that was built by Mario Matteo. And this is actually, I would consider it perhaps the best combination of telescope and instrument in the world for studying the chemical composition of massive globular clusters in our galaxy. So it's a plug plate system where you drill plates ahead of time, and this is the plate I made for 6273. And you plug individual fibers on top of the stars, and out at the other end comes a high-resolution spectrum. So you can either do 256 stars in one order, or you can use the cross disperser like I use, and get, in this case, 6 orders and about 40 stars. So this is the metallicity distribution function of a different cluster that I did on the exact same night with basically the same instrument setup. And if you were to look at, pick a globular cluster at random in the galaxy, measure the iron content of its stars, you would end up with something that looks similar to this. Basically, a single average metallicity with some dispersion due to measurement uncertainty of about 0.05 to 0.1 dex. And here is what I found for NGC 6273. See, not only does it have the expected population, but it has this other group of much more metal-rich stars. Now, this is completely unexpected from past analyses of this cluster, even though some people thought it might have a metallicity distribution, you might expect just an extended or broadened distribution, rather than really two different stellar populations. And because this was a new instrument, I wanted to make sure that there wasn't something funny going on. But if you take two stars that are right next to each other on the color magnitude diagram, plot up their spectra, you can see that the line depths for these more metal-rich stars are always have deeper line depths. So that tells us that these clusters are, in fact, more metal-rich than this dominant population. In fact, just a few weeks ago, I took about 50 more spectra and found that not only are there two different populations and a metallicity dispersion of something like a factor of 2 or 3, but there's this other, very much more metal-rich stellar population that's sort of a trace population. And the full range of metallicities that I find in this, what was once thought to be a relatively simple cluster, ranges from by about a factor of 10, from the metal poor end to the metal rich end. And because there is evidence of at least 3 different subpopulations, that tells us that this cluster was probably very massive when it formed, because that's the only way it would have been able to hold on to the high velocity gas ejected from core collapse supernovae that would have enriched this cluster in iron, while still maintaining a high alpha to iron ratio. So now you may wonder, what do the light elements look like? As I showed in a relatively normal globular cluster, the situation is quite complex. Now, this is again a deceptively simple plot. So here I've plotted the sodium abundance versus the aluminum abundance for stars in this cluster. And the colors differentiate stars in the metal poor or the metal rich population. So you can see that there is a very strong correlation between these two elements. This matches exactly what we observe in other globular clusters. But the really amazing thing is not that there's a sodium-aluminum correlation or that this cluster has first and second generation stars. It's that each of these populations was able to form its own group of first and second generation stars. Now the reason this is really amazing is because we really have no idea how this happens one time in one globular cluster. Yet in this cluster, the same thing has happened twice in a row, all while supernovae are going off, iron's being enriched, and lots of complex star formation processes are occurring at the same time. But what's really interesting is when we look at the heaviest elements. So if I make a plot of something like lanthanum to europium versus metallicity, now the reason these elements are important is because lanthanum, we suspect, is produced almost entirely by what we call the slow neutron capture process. And this tends to operate in stars that are more massive than the stars we observe today. So it's not being produced in these stars, but was produced in a previous generation of stars that had masses of about 1.5 to 3 solar masses. And the reason that that number is important is because it sets a time scale for how long enrichment had to have occurred in order for there to be an increase in the abundance of S process elements. So europium is produced almost entirely by the R process. So if you find stars that have very low lanthanum to europium ratios, that tells you that the stellar population formed very rapidly. Very rapidly. If they're higher, then that tells you that there was much more extended star formation. Now what's interesting is when you compare this with single metallicity globular clusters. If you were to look at almost any globular cluster in the galaxy, you would find stars only in this blue shaded region, which also coincides with the metal poor population in NGC 6273. But as the metallicity increased, so did this contribution from the slow neutron capture process. So that means that there had to have been at least a 1 to 300 million year age gap between the formation of this metal poor group and the more metal rich group. This is something that we don't see really in very many other globular clusters. In fact, there are only a handful of similar cases. But what's really interesting is this particular shape is important because it tells us that this increase in the abundances of lanthanum versus europium is due to almost pure S process enrichment. This is something that we don't see in any other single metallicity globular cluster. So you recall that I said NGC 6273 might have something in common with Omega Centauri. In fact, Omega Cyn actually looks like it may just be a much more complex or extended version of NGC 6273. You'll see that rather than having 2 to 3 different stellar populations, it has 4 to 5 different stellar populations with different metallicities. So keep in mind that in a normal globular cluster, there is only one population, and each of these populations has its own subset of 3 to 5 further subpopulations with different light element abundances. So you might wonder, what do the light and heavy elements look like in Omega Centauri? Well, again, when we plot sodium versus aluminum, or sodium and aluminum together, we again see that there are very distinct correlations between sodium and aluminum. So again, that's not surprising. But what is surprising is that despite the production, or at least 4 to 5 unique star formation events occurring, we actually see each of these different star formation events, which probably occurred over something like more than 500 million years, perhaps as long as 1 billion years. Each of them was able to produce their own set, again, of first and second generation stars. But what's really interesting is that the ratio of first and second generation stars changes with time. In the first stars that formed a large population of first generation stars, so they have a similar composition to the galactic halo. But by the time you get to the second, third, and more metal-rich populations, you can see that this first generation population is disappearing. So there's something unique about these different star formation events that occur in globular clusters that tends to favor the production of these stars that are found only in globular cluster environments. And they become much more dominant over time. And again, just like in NGC 6273, if you plot lanthanum to europium versus the lanthanum abundance, again you find pure S-process enrichment. Whereas if you were to look at a normal globular cluster, you would only find stars down here. So I've only highlighted these 2 particular clusters because they tend to stand out. They're the most extreme examples that we have. But over the last couple of years, we've now discovered that there are at least 9 globular clusters that all share very similar chemical and physical characteristics. So we know that when we look at the red giant branch or the subgiant branch, in particular filter combinations that would look like a single population in most clusters, these show very broad or distinct sequences, which tells us that they've had extended star formation and that they were massive enough, at least at one point, not necessarily now, that they were able to hold on to the ejecta from supernovae and produce multiple generations of stars. We know that their horizontal branches tend to be extremely blue. So you notice that Omega Centauri and NGC 6273 had that sort of curving, falling off shape of its horizontal branch. While this is not unique to these sort of peculiar massive clusters, it is some characteristic that they almost all share. Something that I didn't really talk about, but that seems to be true, is that all of these clusters seem to fall in sort of the top 25% of the most elliptical clusters. In fact, NGC 6273 is the most elliptical or elliptically shaped cluster in the galaxy. Oddly enough, they all, except for perhaps one, have almost the exact same average metallicity. So whether or not this means they were related or if they just happened to form at the same time is still an open question. Another very interesting characteristic is the radial distribution. So you don't just have stars forming with these different populations at all radii in the clusters. We tend to find that the most metal-rich and these so-called second-generation stars form preferentially in the centers of clusters. And the reason this is important is because if you have a cluster that is losing stars due to tidal disruption, the first stars you're going to lose are probably the ones that look exactly like the stellar halo. So even if you disrupted a globular cluster partially, you may not expect to find a population of second-generation stars just out in the halo field star population. And we also find that these are among the most massive clusters in the galaxy. So Omega Centauri is the most massive, 6273 is about the 3rd or 4th most massive, and all of them are on the high mass end. So that clearly tells us something important about how they had to form. And of course, the composition is what's really unique about these clusters. They have very strong S-process enhancements that tend to correlate with metallicity enhancements. So these are all the details that someone like me cares about. But for someone that doesn't work, particularly on globular clusters and care about all the nitty-gritty details, you want to know why should you care. So the reason that these clusters are interesting is not just that they're massive, but the two most massive clusters of this particular subclass are actually very important. So we think that omega Cen is actually the remnant core of a tidally disrupted former dwarf spheroidal galaxy. And we know that M54 is actually currently the nuclear star cluster of the Sagittarius dwarf spheroidal galaxy that is currently being tidally disrupted by the Milky Way and is actually leaving behind a stream and also its own globular cluster population. So whether or not that means that all of the other clusters that have these particular formation signatures were also former dwarf galaxies remains to be seen. But there's sort of an interesting correlation. If you look at the absolute magnitude versus the half-light radius, or basically the size of the cluster, you see that most of the globular clusters in the galaxy just sort of randomly populate this part of the diagram. But these peculiar clusters lie along a very distinct sequence, which is not all that much different than the nuclear globular star clusters we see in other galaxies. So the main takeaway from this is that sort of the prevailing theory at the moment is that these very massive clusters that have these very peculiar chemical compositions may be the core remnants of primordial galaxy building blocks that helped form up, create parts of the galaxy, such as the Milky Way halo. And they may even be the remnant cores of objects such as former dwarf galaxies. So where should we go from here? So this is a relatively simple plot that holds quite a lot of information. So this is a plot, again, of absolute magnitude, which is a proxy for mass, versus the measured iron dispersion in the cluster. So these stars are globular clusters that we've identified as being part of this peculiar class of objects that is able to enrich itself with subsequent generations of stars with different iron abundances and different heavy element abundances. So one of the questions we want to know is, what separates two clusters of similar masses that took very different evolutionary paths? In other words, how does a cluster like NGC 6273 form when there are other clusters of very similar mass, such as M13, that have similar light element abundance variations, that have very blue horizontal branches, but they were not able to form subsequent generations of stars that had added iron or that had these very high S-process enhancements? In other words, they only formed, all these stars down here were only able to form basically a single formation event. Whereas all of these were able to continue self-enriching themselves with the products of massive stars and also probably intermediate mass stars. And we also want to know how many of these massive clusters with S-process enhancements actually exist. So we've found 9 so far. And we also want to know, are there any more? So we've identified at least 13 globular clusters that have very similar characteristics. Some of them are relatively elliptical. They all have very blue horizontal branches. They're in the same sort of mass range that we would expect to find these clusters, but no one has yet measured their metallicity dispersions. So this is actually a great project for the M2FS and hectoshell instruments on the Clay telescope and MMT. And this is one of the projects that I'm working on now. But a final question we want to know is, what is the minimum mass at which a cluster can self-enrich itself with heavy elements? In other words, is there a cutoff at which you can no longer have clusters self-enriching themselves with heavy elements? And this is a very key question that we need to answer, because it has important implications for the original mass function of globular clusters and how star formation actually proceeds in massive stellar systems. So I thought I would just conclude by coming back to some of our original questions that we asked. So how did the early universe and galaxies form and evolve? Well, we know and we've established that globular clusters were among the first objects to form in the galaxy, or in the universe. And we know that they created stars with very unique chemical compositions that we don't really see anywhere else, but if they do form, if they were contributors to other populations, perhaps the galactic bulge or the galactic parts of the galactic halo, we should be able to detect them. And we know that second generation stars are not found in significant numbers, but the key here is that first generation stars might have been. So as I said, these first-generation stars appear chemically indistinguishable from your average halo field star. And what we think happens is when a globular cluster forms, first it forms these stars at all radii, then eventually material gets funneled towards the center of clusters, where these much more enriched populations form. And because those sit at the center of the potential well, it's much harder to disrupt them and toss them out into the galaxy. So this could be an explanation for why these second-generation stars are not seen in the general field population. And also we want to know, how were galaxies assembled from primordial clumps? Well, we've now established that some of the most massive galaxies may actually be remnants of these more massive systems that helped create galaxies like the Milky Way. However, one of the biggest problems with this is we don't yet know how to get rid of the dark matter halo. So if we assume that these massive systems formed in a dark matter halo, the clusters that we observe today, even clusters like Omega Centauri, do not have any dark matter. So this is a question that really needs to be addressed by theory, or if we can find some systems that sort of merge between globular clusters and dwarf galaxies, because dwarf galaxies often have dark matter halos, but globular clusters don't. It should really help us figure out what the transition is between just a massive globular cluster or a dwarf galaxy. And again, we want to know why are globular clusters important for observational astronomy. So we've now established that even the simplest globular clusters are relatively complex and have undergone several different star formation events. But even the most massive ones and the brightest ones that we're likely to observe at high redshift were probably much more like Omega Centauri or NGC 6273. So not only do they probably have large light element variations, they may have factors of 10 or 100 variations in their heavy element abundances. And this can have important and strong effects on integrated light spectroscopy, interpretations of color magnitude diagrams, or simply understanding the colors of globular clusters that you see in other galaxies. So basically, the problems we're trying to solve now are how do we link the formation of all these objects? So what's interesting is that some of these clusters down at the low mass end appear to actually not even have light element variations. So rather than there being two different populations of globular clusters, are there actually three? And is there a way to reconcile how nuclear globular clusters form in dwarf and other systems or in other galaxies with these massive globular clusters that have very peculiar chemistries and seem to have been much more massive in the past? So how do we figure out how these populations link together? And that's basically where we are, sort of the state of the field at the moment. And I'm hoping that by using M2FS and hectoshell and identifying exactly how many of these clusters there are and what their peculiar chemistries are and whether there are any different signatures, that we can really hope to solve some of these problems. And that's all I have.
So the talk is open for questions. Yes.
Are there major temperature differences between first and second generation?
Sorry, can you repeat the question?
So, are there major temperature differences between first and second generation stars?
So the question is, are there major temperature differences between first and second generation stars? Do you mean like effective temperature?
Yes.
In essence, yes. So part of, let's see if I can bring it up. So yes, because obviously color is related to temperature. So there are small temperature differences that if you have very high quality data you can sometimes detect. And it's not just that there are color differences because they have different light element abundances. It's actually not just carbon, nitrogen, oxygen, it's helium that has a large effect because that really changes the structure of the star and the mass of the star. So if you have a helium-rich versus a helium-normal star, the helium-rich star, if it formed at about the same time, will be a much lower mass because it evolves so much more quickly. So when you look at stars on the red giant branch, sometimes we can actually pick them apart. And the difference is not large, it's maybe something like 25, 50 Kelvin, sort of within the measurement error, but short answer, yes, but it's difficult.
Just to be clear, what you're calling first generation is actually made up of reprocessed material from yet an earlier generation, right?
Presumably. So population 3 stars form, they blow out material. Because these aren't zero metallicity clusters, obviously. So.
And if I could just ask another
Sure.
question. So the reason these look so very virialized is that they've undergone considerable amounts of dynamical friction and other essentially collisional events within the structure of the
Right.
of the
Talking about like relaxation.
Yes. So we have enough relaxation events, so these things would have been very different billions of years ago, but now look relaxed.
Right.
Right.
So so most of them that's true. So Omega Centauri, its relaxation time is about the same as its age. So it's not quite relaxed yet. So that's why it actually looks very large. It's about the size of the full moon on the sky. So it's a very big object. I mean, it's close too. It's 5 kiloparsecs. But it has it's not a very dense core. And in fact, most of the clusters I talked about aren't core collapse. So whether or not that has an effect on how the cluster evolves chemically, even though that happens much later, because the compositions that we see today are how they formed early on in the cluster's evolution. But it's an interesting question and one that we can address when we actually find more of these objects.
Dimitar?
How possible is it that some of these massive globular clusters had an accretion history of their own, that they've accreted other smaller globular clusters?
All right, so the question is, could these massive globular clusters have either accreted other globular clusters or field stars or something else? That was one of the original ideas for an object like Omega Centauri. Perhaps it was 3 or 4 globular clusters that merged together. That's never strongly been addressed. The conventional wisdom is that that's probably not what happens, both because there are the collisional cross-section of globular clusters in the halo is small. Now, if you had them forming close together initially, that's probably the more likely scenario. If you actually look at the detailed kinematics, rotation, or just radial velocities of the different stellar populations in a cluster like Omega Cen, you actually don't see any differences. And that's been used as sort of an argument that probably these clusters self-enriched and formed very distinct multiple generations of stars rather than grabbing different generations or different clusters that form separately. And also because the metallicity range tends to not be very large. So there is one object that I didn't talk about called Terzon 5. It also has multiple generations of stars with different metallicities. But rather than the gap being a factor of 2 between the different populations, it's more like a factor of 5. And so that could be a candidate for a cluster that actually did accrete other material.
I think Ramesh was next.
Yes, we've got these different kinds of globular clusters. The simple ones, 2 populations, and up to 5 populations.
Right.
So are they segregated in any way by radius in the
radius in the
Milky Way?
galaxy?
In the galaxy, yeah.
Not particularly. The clusters that have blue horizontal branches tend to have more populations, and those tend to be farther out in the halo.
Farther out, okay.
Right, so they were less disturbed, I guess. So there's actually there's somewhat of a metallicity gradient with globular clusters in the galaxy. So those that are close to the center tend to be much more metal rich, and they have much smaller star-to-star variations in their light elements. So they would only have probably 1 or 2 populations, whereas those that are farther out tend to have many more. But whether hard to say if there's a direct connection. Was it just because that those were able to form in a lower density environment where they weren't bothered? It's hard to say.
Igor?
Yeah, I have a question regarding this red and blue globular clusters. So most of these you've shown, they're supposedly metal cores, so on the blue end.
Right.
First, is there any evidence of something like this happening in the red end? And second, you've shown this first and second generation of stars.
Mm-hmm.
Can you think of any mechanism that would produce this aluminum and sodium enriched stars on a galactic scale at high metallicity regime, like galactic bulge or whatever?
At high metallicity, it becomes difficult to actually increase the sodium and aluminum abundance by such large amounts. So at low metallicity, if you add a little bit of sodium and aluminum, because there wasn't much there to begin with, you can quickly increase the ratio of, say, sodium to iron. At high metallicity, it becomes much harder, and actually the production tends to not favor, the nucleosynthesis tends to not favor overproduction of elements like oxygen, sodium, aluminum. Because the temperature is reached in the center, in the regions of stars where these nuclear processes are occurring, tends to be lower, which tends to favor production of lighter elements, and you just tend to not produce as much sodium and aluminum. And also because the mass loss rate increases in these stars. So they tend to lose too much mass before they've had enough time to synthesize all these heavier elements.
Josh?
So you mentioned Terzan 5. I was going to ask you about that. That's a cluster that has the most remarkable population of millisecond pulsars,
Right.
and neutron stars, as does 47 Tuc, of course.
Right.
So is there a strong correlation between metallicity and numbers of generations? I would have
Oh, metallicity and numbers of generations
Yes.
of stars?
Presumably there must be, because as you have successive generations, you've increasingly polluted the cluster with heavier elements from which that next generation comes.
So the more metal poor clusters tend to have more generations.
Okay, but Terzan 5 you mentioned has...
So Terzan 5 is sort of an exception.
That's a very metal-rich cluster, as I understand it.
Right, so, let's see, do I have... No, so the average metallicity bracket FEH of the clusters I was talking about today are mostly around -1.5. Terzan 5 is about a factor of, the most metal poor population, Terzan 5, is a factor of 5 to 10 more metal rich. So,
Right, yeah, it's a very metal-rich.
and it actually extends up to FEH of plus 0.5. So, you know, more than about a factor of 3 more metal rich than the sun even. So Terzan 5 is sort of the exception. And it may be analogous to something like G1 in Andromeda, which they think looks like Omega Cen, but is a lot, factor of 10 more metal rich.
But the fact that it's so metal-rich with 5 generations, I'm guessing has something to do with its very high neutron star population.
Possibly. So part of the problem with Terzan 5 is because it's under such heavy optical extinction,
Yeah,
we can't measure yet. This is a project for GMT.
yeah.
We can't actually obtain ground-based spectra, or really any high-resolution spectra in the optical regime where lines of lanthanum, europium, etc. exist. So once GMT comes along and GClef, that'll be a great project. And really from there we'll be able to know whether or not this is the same sort of formation mechanism that's driving something like Terzan 5 versus Omega Cen, or whether, say, Terzan 5 happened to accrete one or two other objects while it was forming. So that one's found in the bulge, where so is NGC 6273. But many of the other ones tend to be formed outside the bulge.
I have a couple of questions.
Sure.
So you made a number of comparisons with the halo stars, but you've shown a significant effort of getting spectra of globular cluster stars.
Right.
Is the situation with spectroscopy of halo stars comparably good? In the sense, would you see evidence for all of these structures in the halo stars if they were there?
You mean would you find like second generation stars
Yes.
if you look? So it's difficult to get high resolution spectra for a lot of halo stars just because they're spread out, they tend to be far away, so it's not very efficient. But one of the things that has been done is the Sloan survey has low resolution or medium resolution spectra of lots of halo stars. And they've used the carbon, I think it was the CN and CH bands, to look for variations in the carbon abundance. And they know that if they find stars of the same evolutionary state, but they have a wide range of carbon abundances, that tells you that first and second generation stars are present in the halo. And in fact, we do find second generation stars in the halo with a ratio of about 2% first generation stars, 2% second generation stars and 98% first generation stars. So the idea, I think I have a plot of this somewhere. I guess I moved it. Well, anyway, because globular clusters, the second generation stars form very close to the cluster core. We don't think that they're easily stripped off. so it's probably difficult to tidally strip them and put them in the halo. And the globular clusters that were disrupted, that could have formed the halo, were probably disrupted before they could have actually formed these multiple generations of stars.
Okay. My second question has to do with is inviting you to speculate. So you commented on multiple generations of enrichment, of significant mass loss. So what would something like one of these globular clusters have looked like when it was 500 million years old?
Yeah, that's a very good question. So one of the things that could possibly be tested with something like JWST is to actually look at higher redshift and try to measure the mass function of sort of proto-globular clusters and see if it's somewhat equivalent to the mass distribution that we see today. So we don't, one of the big questions is, were these massive clusters I was talking about, were they actually formed at the centers of dwarf galaxies, or were they able to form sort of on their own as something between a globular cluster and a dwarf galaxy? So if you're able to think back to a few hundred million years after the Big Bang, there's actually an interesting test you can do. I don't know why it's not showing up. See if this works. Oh, well, okay. I lost it. Yeah, there's actually, in the integrated light, because the spectrum of an integrated population, let's see, I think I should be getting close. Sorry, these are just different. Yeah, so in integrated light, the spectrum of populations that have different ages will look different. So if you have if you're forming these different populations and they're separated by an age of something like 100 million years, you may not be able to pick it up. But if they're separated by 10 million years, you can perhaps pick up some of these emission lines. And that will at least give you some sense of when these clusters were forming, how long the star formation was going on in these clusters, and hopefully that can give you some information about what these clusters might have looked like early on when they were forming.
So let's thank Christian again.